over 4 beta sine 2 beta t plus 1 over 32 beta sine 4 beta t plus some constant. There it is. There's a lot to keep track of, right? There's a lot that you have to keep sorted out here. Yes? Okay, so when we started class at the very beginning, I said there are 2 formulas we need to be comfortable with. That if you have sine of a linear expression, the antiderivative is cosine of that linear expression, but you have to scale by negative 1 over a. Similarly, if you have cosine of a linear expression, then you scale by 1 over a, not negative 1 over a, and then you have sine of ax plus b plus c. This is the one I'm using, because this right here is like an ax plus b. But our variable, c, the x is our t, right? And 4 beta is a constant. 4 beta is the a. So I do 1 over a sine of the linear expression. Got it? Good. Thank you for asking. Anything else?
I have a question.
Yes.
I noticed whenever we did the initial separation out here, you saw the cosine squared.
Mm-hmm.
Would that happen if you increase every increment by an even number?
Yeah. So if it was like cosine to the 6th, you mean?
That would be cosine to the 4th, and then we would just have to keep doing it essentially like we did here.
It would be cosine to the it would be cosine squared to the 3rd. Yeah. So if we did, if we were doing this integral, which is actually a homework problem, I'll do that without the beta to make it a little bit nicer. If we were doing that, then is that what you were asking? Like if we did 6, then this would be cosine squared cubed, right? Which would be 1/2 1 plus cosine 2x. That's me using the power reducing formula cubed, right? Still with me?
Yeah.
Then I would cube the 1/2. When I cube the 1/2, it would become 1/8. I could bring the 1/8 out of the integral, and then I'd have to do 1 plus cosine of 2x cubed dx, right? Then I have to cube that. If I cube that, I get, anyone know what I get when I cube that? Well, you get a 1, and then you get it should be pluses the whole time. It should be pluses. Plus 3 cosine of 2x plus 3 cosine squared 2x plus cosine cubed 2x dx. Do you believe me that that's what you would get? Do you all believe me? If you cube that out, if you took this times itself, right, 3 times, you would get that. Now, can you do this? Yes. Can you do this? Yes. Oh, I erased it. Yes, the formula I just... Can you do this? No, but yes, because then we could do the power reducing on that, right? So you power reduce that one. Okay, could you do this? Cosine cubed, how do you do that? Peel off 1 cosine and do it the first problems we did. You see? This is a homework problem, actually. So, but I've kind of laid it out for you now. Cosine to the 8th would just be torture, because that would be cosine, right, that to the 4th, and then you rewrite it to the 4th, right, to the 4th, and then when you expand that to the 4th, you're going to get a disaster, because you're going to have a constant. When you do that to the 4th, you're going to have a constant, you're going to have a cosine term, you're going to have a cosine squared, you're going to have a cosine cubed, and a cosine to the 4th. And the cosine of the 4th is going to require that formula twice. The cosine squared would require that formula once. So cosine of the 8th is just pure torture. Anything past that is just, yeah. But cosine to the 6th, everybody should have to live through cosine to the 6th. That's at least one time as a Cal 2 student, you should go through cosine to the 6th. And if you're real venturous, go out and try, you know, sine to the 6th or sine to the 8th or something like that. They all suck. Okay, we good? All right, we're like halfway through. Remember this section I told you is like 2 parts, right? What we do today and what we do next class. We're halfway through today's part. Now we just have to deal with the tangent and secant. Integrals that have tangent and secant together. So one thing we should be aware of, this right here. Just like I put on the board in the beginning of class, we know how to do antiderivative of sine with the linear expression inside and cosine with the linear expression inside. We have to scale. Same thing when you have secant squared, or, so if you have secant squared and this is linear in here, you have to scale by 1 over a. What's the antiderivative of secant squared? Tangent, right? Because the derivative of tangent is secant squared. Similarly, if we have a secant and a tangent together, the antiderivative is secant. Why? Because derivative of secant is secant tangent. So we have to scale as well. So we're not going through that. I'm just pointing out that we should be somewhat comfortable with that idea. All right, let's get to some examples here. There's a strategy as well. There's steps like what do you do, okay? But I like to just get right into it. Here's 2 examples. These problems are extremely similar to one another, but the way you attack them is completely different. Well, not completely. Yeah, completely. We're still going to use trig, all right, on both. All right, so look at that one. So with sine and cosine, right? When I was sitting here thinking, I'm really going to start using this. Okay, when I was sitting here thinking about it, right? I was peeling things off, and I was saying, okay, if I peel off a cosine, then u has to be sine. If I peel off a sine, then u had to be cosine. Here, what would I peel off? What makes the most sense to peel something off here? The thing you peel off needs to be the derivative of something you know. Secant squared x, right? What would happen if I peel off a secant squared? I write secant squared x dx, right? So I have peeled off 2 factors of secant, right? Secant squared x dx. What is that telling me my u is going to have to be? What derivative do you take to get secant squared? Derivative of what? Tangent, right? That means my u is going to need to be tangent x. If I peel off a secant squared, right, my u is going to be tangent. Can I rewrite the rest of the integral in terms of tangent? Well, that's already in terms of tangent, right? Can I rewrite secant squared in terms of tangent? I erased it, but yes, right? You can, using the Pythagorean identity that I had on the board earlier. What's the relationship between tangent squared and secant squared? Secant squared x equals 1 plus tangent squared x. So I'm going to go right from here. I'm going to go tangent to the 4th x, and then rewriting the secant squared x. You can write it as 1 plus tangent, or 1 plus tangent squared or tangent squared plus 1. Does not matter what order you go in, because it's addition. Let's back up. Let's think about this again. I had tangents and secants mixed up, right? I had secant to the 4th power. And what I'm thinking, like 3 steps ahead, I'm thinking if I peel off a secant squared, I'll still have an even power of secant here, won't I? Peel off secant squared, I'll still have secant squared there, and then I can use Pythagorean. I can rewrite this in terms of tangent. Then all this junk will be tangents, which is what my u is going to be, so all this will be u's, and my du will be sitting there nice and pretty on the outside. Now, what if this had been secant cubed, like the next problem? Could I have done it? I peel off secant squared, what would be here? Just secant. And I don't have Pythagorean with just secant, unless I bring in roots like Chris suggested with that other one. So that we would not want to do that. But this one works, so let's keep going here. My u is going to be, who needs help? Anyone need me to explain something? No? This is going to be for us u to the fourth plus 1 du. Okay. U to the fourth, u squared plus 1 du. And that I can just distribute through, right? There's no squared or anything on there. So I can just push that through, u to the sixth plus u to the fourth du. Antiderivative now is just power rule, 1/7 u to the seventh plus 1/5 u to the fifth plus a constant. And now just replace your u's with tangent. 1/7 tangent to the seventh x plus 1/5 tangent to the fifth x plus c. There we go. So in the steps that I'm not showing you, it says if you've got tangent and secant together and your secant is even, peel the secant squared off and then go rewrite this using Pythagorean, right? The steps are there. That's if the secant is even. Now, let's see what happens when the secant is odd. So let's do that. So can we peel off secant squared again and be able to get anywhere with it? No, right? Pardon me? Oh, it's tangent to the fifth. Yes, thank you. Sorry, I didn't notice that was different, but yeah, that makes a huge difference. Okay, now they're both odd, right? They're both odd. Well, I cannot peel off a secant squared. If I do peel off a secant squared, I'm left with a secant, and I can't get that in terms of tangent. We talked about that a second ago, right? Okay, can you peel off a tangent or a tangent squared? Well, whatever you peel off has to be the derivative of something, right? It has to be the derivative of your u. So when you peel off secant squared, you're doing that with the intention that u is going to be tangent. I can't peel off tangent, right? If I peel off tangent on the back side of this, right? If I put tangent x here, dx, and make that a 4, that doesn't help me because that's not the derivative of something, right? So that doesn't help. So what can I do? You can peel both. Yeah. So when we peeled off secant squared, it was because we knew the derivative of tangent was secant squared, right? If all we have to work with here are secants and tangents, think about what's the derivative of secant? Secant x, tangent x. Can we peel off a secant x and a tangent x? Yes. Let's do that. If we peel off a tangent, we're going to have tangent to the fourth x. If we peel off a secant, we're going to have secant squared x. And then we peeled off one of each, right? So I'm going to put secant x, tangent x. Those are each of the factors I peeled off, right? So I peeled that off, and I'm thinking to myself that u must be what then? Secant x, right? If I'm going to peel off a secant x, tangent x, then that means my u needs to be secant x. And so the question becomes, can you rewrite everything here in terms of secant? Well, that's already in terms of secant, right? Tangent to the fourth, can you get that in terms of secant? Well, you can use Pythagorean now, right? Because this is an even power. So I can rewrite that as tangent to the second, right? Tangent squared x squared, that's tangent to the fourth. Leave secant squared x alone. Leave secant x tangent x alone, right? And how do you rewrite tangent squared? You go to the Pythagorean identity, solve it for tangent, and you get what? Secant squared x minus 1. All of that squared, then secant squared x, then secant x tangent x dx. Rewriting that That's all I did, right? Just rewrote that. Now let's go ahead and make our substitution, rewrite everything, and we should at the end of this have a nice polynomial. So now my basic u sub. U equals, what's my u? Secant x. The derivative of that is secant x tangent x dx. And if I do that, my new integral becomes u squared minus 1 squared times u squared times du. So u squared minus 1, all of that squared, times u squared, that is the derivative of u. How many times have we used basic u sub today? Every time we did a problem, right? So this is why I've been saying to you, like, this class builds on itself because, right, at the very end we're using power rule. Within the problem we're using basic u sub, but we're now incorporating all these other techniques with it as well. So, you know, we just have to get comfortable with this stuff, all right? Okay, integral, let's see. I'm going to expand that, right? I'm going to go ahead and multiply that out. I'm not going to show the work. U to the fourth minus 2u plus 1. That's what happens when you square that. Then you still have u squared du. Now you can pass the u squared through. What did I do? Oh, yeah, it's 2u squared. Thank you. I'm glad y'all are paying attention. Okay, now distribute through u to the sixth minus 2u to the fourth plus u squared du. Oh, it's just a little left. Power rule on those, right? No more integral sign, 1/7. Okay, u was what, secant? Yes. Secant to the 7th x minus 2. Oh, wait, I need to do an antiderivative. Hello. 2/5 secant to the 5th x plus 1/3 secant to the 3rd x plus c. I think that one's done too. I'm going for it again. Overcompensated. Did the Cowboys play yesterday?
Yeah, they lost.
My best friend is a huge Cowboys fan. All I've been hearing is talking about Super Bowl and stuff. I was like, Cowboys will always be the Cowboys. They'll always find a way to let people down. Okay. Yeah? Now, we're going to start looking at some integrals now that involve tangent and secant, but you don't do anything like we just did. Just to kind of show you that, you know what, there still is, like, we're still tip of the iceberg here in terms of, like, what we can be presented with. So let's look at this very simple looking integral, the antiderivative of tangent. Never talked about that in Cal 1, did you? Right? Like, we know what the derivative of tangent is, it's secant squared, but what's the antiderivative of tangent? We know the antiderivative of sine, right? And cosine, but we never talked about the antiderivative of tangent. It seems like we should have talked about that in Cal 1 maybe, right? The reason we don't do it in Cal 1 is because it's not that straightforward. I mean, it's a little straightforward for us now, but like in Cal 1 it wouldn't have been. So what is it? Well, you can't peel anything off, right? I mean, it's a single tangent. Like, what are you going to peel? There's nothing to peel, right? So the technique here is to, and this is a good technique whenever you're like stuck and you don't really know where to go, is just to rewrite everything in terms of sine and cosine. Now, like I said right before I started this, This is a problem where we're not going to use the techniques we just used, where we're peeling things off and thinking, what would my u need to be? I'm just going to look at that and just start over from the very beginning. Basic u sub, does basic u sub work? Do you see something in its derivative? Yes. What's the something? If you let u be sine, the derivative is downstairs. You don't want that, right? So you got to go the other way around. U is cosine, derivative's upstairs. That's okay. So let's do a basic u sub, right? U is cosine x. What's the derivative of that? Negative sine x. You're off by sine, right? So negative du is sine x dx. So the entire numerator gets replaced with negative du, and the denominator gets replaced with u. So it looks like this. Integral, I'll take my time. Negative du is on top and then u on the bottom. Do y'all agree that's me just rewriting everything? I'm 0 for 3 today. All right. This is the same as a negative in front, right? 1 over u du. Just sliding that du off to the side. And that was to help you see it, right? What's the antiderivative of 1 over u? Natural log, right? Absolute value. And I still have a negative out front. Negative natural log absolute value of u plus c. And what was u for us? Cosine. Negative natural log of cosine x plus c. There it is. Now, on your formula sheets, since you have yours, can I look at it real quick? If you look at reference page 6, formula 12, you'll notice that a lot of the common integrals that we run into are there. In fact, this one's there. Do y'all see it, formula 12? The antiderivative of tangent, do y'all see it? Is that the answer? It's not. It looks different, doesn't it? So I want to explain why it's different. Because there's that property of logs. You look at that negative as a negative 1 out front, natural log, absolute value of cosine x like this, plus c. And do you remember that property of logs that if you had natural log of x to a power, you could bring the power down and make it n natural log x? That power backwards. Let's do that. That property backwards. Take that negative 1 and push it up here, and it becomes natural log absolute value of cosine x, and this is where notation is shitty. It's that to the negative 1. Okay, that is not the inverse cosine function. This is cosine to the negative 1, which really means 1 over cosine, which is secant. So you get natural log absolute value of secant x, and that's what's on your formula sheet, right? Okay, so I just want you to see that's why it looks a little different. How are we doing on time? 10 minutes? Let's see if we can do one more, two more, one more. One more. So the next problem I'm going to put up here is historically famous. This is a famous problem because it's so difficult. And let's just see why it's bad. Well, first of all, we don't know what the antiderivative of secant is, right? We know the derivative of it is secant x tangent x. We know that, but what's the antiderivative of secant? Well, if you just rewrite it in terms of sine and cosine, this is integral 1 over cosine x. And there's where you run into a problem because you can't do a basic u sub, right? What's your only choice for u if you're going to do a basic u sub? Cosine x, and the derivative of that's sine x, and it's not even there, right? So you can't do a u sub. Integration by parts won't work either. If you try integration by parts, it won't work. If we tried integration by parts, let's just think about what we would do if we tried it. Integration by parts. I would have to make a table. I'd have to choose a u and a dv. I'd only have one choice for u, and that would be secant x. And that would make dv have to be dx. That would be my only approach. And then when I take derivative of that, I get derivative of secant x is secant x tangent x dx. And when I do the antiderivative of 1, I get 1/2 x squared. That's my v. Y'all following me? Integration by parts? Ultraviolet minus voodoo. So ultraviolet, fine, minus the integral. Look at my voodoo integral. Terrible. Because I've got secant, tangent, and now I've got a polynomial little expression in there as well, which makes it even worse. So this is not going to work, okay?
Why would the b be a 1/2 x squared? Wouldn't it just be x?
Yeah, I don't know why I put 1/2 x squared. I'm sorry. Thank you. I don't know what I'm thinking. I just had a brain fart. This is 1, this is x. Still, it doesn't help because I now have a polynomial stuck with this, right? Okay. So how do you do it, right? Well, it turns out that the way you do this is by someone just like figured it out, okay? Somebody just figured it out.
Guessed over and over.
Just, yeah, somebody, we don't know exactly how to, and it wasn't a guess, it was just, I don't know how this person sees this, but let me show you what they did. They said, okay, I'm going to take this secant x, and now trust me, this is somebody who was like could not sleep, like this was, I don't know, I'm sure this took months, years, perhaps. Someone finally came up with this. I don't know. They decided to multiply this by 1, okay, by 1. And what they decided to multiply by was secant x plus tangent x over secant x plus tangent x dx, right? That doesn't seem very natural, does it? No? But I'm allowed to do it, right? You can multiply anything by 1. Okay, so now if you look at that, and now let multiply. That's a fraction, right? Times a fraction. How do you multiply fractions straight across? My numerator becomes secant squared x, right? You're multiplying here to here. And then you get plus what? Secant x, tangent x. Over, the bottom is what? Secant x plus tangent x dx, right? Why did they do that? I don't know why they did it, but do y'all see how nice it is now? It looks horrible, but do you see it? Who sees it? Now you can mess with top, but plus. It's plus right here. Plus in here. Do what? Basic U sub. Do you see it? What's U? The bottom. The bottom. Look, if you do this, let U be secant x plus tangent x. What's the derivative of that? What's the derivative of secant x? Secant x tangent x plus what's the derivative of tangent x? Secant squared x, right? dx. Do you have that somewhere? Yeah, that's your numerator. Right? That's the numerator. Now, look, I would never give you a problem like this. I'm just trying to show you that, like, we can come up with techniques all day and all these different approaches, but there are still integrals that are just not easy to get. So if I do that, what's my new integral going to be? All of this is du, right? That's du, so we put that on the side. And then this is what? U? 1 over u, right? So antiderivative of 1 over u. Natural log, absolute value of u, right? What's u? Secant x plus tangent x. Now, do you see that on your formula sheets? Yes. It's there, right? So on your formula sheets, I want everyone to realize this when you get to a test. I expect everyone here to know what the antiderivative sign is, right? And cosine. You shouldn't need a formula sheet for that, all right? But the other 4 trig functions, tangent, secant, cosecant, cotangent, right? Those 4 integrals, those 4 are on your formula sheets, okay? You can use those. I've shown you how to get tangent, now I've shown you how to get secant. The others we could get doing different, but I'm not going to show you all of them. All right, we are out of time. The plan is to come back and do a little bit more of this. I have not looked at, are there any extra worksheets that I passed around? Are there any extras? Is that an extra? Yeah. Okay. You got one. All right. Everyone got one of these? I haven't looked at these. These are out of a different book. But look at number 10. Look at number 10. You see it? Cosine to the sixth. I told you. Now I'm not seeing any. I'm not seeing cosine to the eighth, so that's good, or sine to the eighth. So I would recommend that you do as much homework as you can out of your homework assignment, right, for this section. You can't do it all, because remember, there's two parts to this. I don't remember where it breaks off. I'll shoot everybody an email later on today. But it's you'll know when you're doing your homework, when your integrals no longer have trig functions and they start to have square roots in them, that means you moved into the next topic for this class. So just all the stuff that has trig stuff in it, try and see what you can do. And then you can work on that worksheet. We'll have a quiz next class in the beginning. I'm thinking I'm going to do it this way. Give you 2 problems, let you choose. So one of them, integration by parts, the other one, trig integral. And so you'll have 2 problems. You can only do one, but at least you have 2 to choose from, right? Okay, and it'll be quick. I mean, we can't sit here for 30 minutes taking a quiz. So bring your homework with you and your notes, okay? It might be nice and let you use them.
So,
Yes.
no, on the integrate by parts homework.
Okay.